Nuclear fission Rankine-style steam plants provide approximately 22% of the total electric power to the United States. And about a dozen different designs of these thermal fission plants have been commissioned. Each of the different designs using a different combination of what are called a moderator and a coolant, which we'll look at in a little bit. The steam generator in a nuclear fission plant uses heat produced via a nuclear reactor. When a large fissile atomic nucleus absorbs a neutron, it may undergo nuclear fission, which means it will split into two or more lighter nuclei. So we've got an atomic nucleus. It'll absorb a neutron that can cause it to split into smaller and lighter nuclei. When this occurs, when this nuclear split occurs, kinetic energy, gamma radiation, and free neutrons are also released. That free neutron being critical. That free neutron can be absorbed by other fissile atoms, other nuclear fissile atoms, and therefore that free neutron can trigger further fission events. And when it does that, this is called a nuclear chain reaction. One atom splitting, releasing a neutron, that neutron being absorbed by another atom, it splitting. This is called the chain reaction, nuclear chain reaction. In a controlled reaction, one neutron from each fission event, a fission event being a splitting of an atom, one neutron from each fission event should interact or will interact with another fissile nucleus. If we have fewer than one neutron from each fission event reacting with another fissile nucleus, the reaction will eventually fizzle out. But if we have more than one neutron being released, it will cause multiple atoms to go into chain reaction, and then those atoms will cause even more, and we get this kind of avalanche effect, and eventually enough heat is produced to melt the structure. So the key at running one of these Rankine-style thermal energy nuke plants is you want to extract the heat from the nuclear reaction, but you have to do it in a controlled manner. You have to have that reaction precipitating in a controlled manner. And the where that's done is what's called the nuclear reactor. They have four essential components inside one of these fission reactors: fuel, a material called a moderator, a material called a coolant, and a third material that makes up what's called the control system. Modern reactors for fuel need fissile materials, radioactive materials that will split. Modern reactors use uranium-235 or plutonium-239. The fuels for these usually is in the form of ceramic pellets, uranium dioxide or plutonium dioxide. UO2 is what it is, UO2, or plutonium dioxide is PuO2. Those are the two major fuels, this one occurring naturally, this one only occurring as a process of a chemical reaction or a nuclear reaction involving uranium dioxide. So we can mine this and process it. We get this from these style nuclear reactors. So anyway, they're both pelletized in these ceramic pellets, and they're placed into metal tubes. And that's what you will call a fuel rod. So everybody talks about nuclear fuel rods. And really what a fuel rod is a metal tube filled with ceramic pellets of UO2 or plutonium dioxide. A typical reactor might have 100 tons of these pellets inside of it. So relatively small amount of fuel as compared to the millions of tons of coal that gets burnt. 100 tons, not so much. The moderator is a material that is used to slow down the neutrons in a reactor, and this maintains the chain reaction. The main requirement of the moderator is that it reduces the speed of the neutron and doesn't absorb them. The purpose of reducing the speed in the nuclear reaction is to limit the velocity to that which is capable of sustaining a nuclear chain reaction. So if the neutron is moving too quickly, it will simply bump off an atom, not causing the chain reaction to occur. If it's moving too quickly, most of the energy will actually be in diverting the angle at which the two surfaces interacted, or the two particles interacted, and again, a nuclear event won't occur. So there's an optimal speed that these neutrons have to be flowing at, and moving at, and the property of the moderator is to control that. The majority of nuclear plants have what are called light water reactors, meaning that the moderator inside of this reactor is just normal water. Other choices include heavy water or deuterium and graphite. The coolant is kind of oddly named, I guess. It's the liquid or gas medium that's used to extract the heat from the reactor core. It can be a gas. In some designs, the coolant is the moderator, they're the same fluid. And then finally, to kind of control the heat output, there is a neutron absorbing material such as cadmium or boron that is shaped into what are called control rods that can be moved in or out of from in between the fuel rods. So now that we know the terminology, kind of what's happening here is we've got these uranium fuel rods. They're submersed in the moderator fluid, deuterium, or normal water in a light water reactor. There is a nuclear fission event that will occur in this, and neutrons are coming out of these UO2 or PuO2 ceramic pellets. They will cause reactions inside the other material in the fuel rod, and then also, the neutrons will come out of the fuel rods, and they can be absorbed by these other red fuel rods, causing further nuclear reactions, and that's the chain event. The liquid inside of here, the moderator, controls the speed at which the neutrons can move through the nuclear reactor to put them at the appropriate speed such that they cause a chain reaction. We want that chain reaction to occur. Then these tan elements are these control rods. And physically what the control rods do is they move in and out between the fuel rods, and they absorb neutrons. So if they're in there, they're absorbing all the neutrons, and it shuts down the reactor. If they're pulled all the way out, the neutrons are free to propagate. It speeds up the chain reaction, more nuclear fission events occur. And so you can move those up and down to change the amount of nuclear fission events that are occurring. In this diagram, this is not a light water reactor. They're using a graphite moderator in here. So these are just graphite materials. You see that there's a graphite material on either side of the fuel rods, in this case uranium fuel rods, and that graphite is intended to slow down the speed of the neutrons. In most reactors, that's actually water. In this reactor, we see that there's a cold gas in, hot gas out. A lot of times this is just water, although it's a high pressure steam, kind of high temperature thing, just like in the steam cycle plants. And then there's a lot of times there's a heat exchanger, although not always, right? There's not always this heat exchanger here. So that's kind of the typical behavior of the reactor core inside of a nuclear plant. Like I said earlier, there are about a dozen separate thermal fission designs that have been constructed and operated worldwide, and they differ really primarily in their choice of the moderator used and the coolant used. The majority of the world's nuclear plants use ordinary or light water under high pressure as both the moderator and the coolant, with the pressurized water reactor being the most common implementation. It's called a PWR, and so we've got a diagram of how the whole PWR plant works, not just the core here. The core of the PWR consists of about 100 fuel assemblies held between a top and a bottom plate. We're talking about this area right here. With each fuel assembly consisting of a cluster of a few hundred long, thin fuel rods. So we've got fuel assemblies, there's about 100 of them. There are about 100 fuel rods per assembly. The open core construction here allows water to flow at a high pressure past these fuel rods, It's absorbing the heat from the fuel rods, from the nuclear reaction occurring in the fuel rods, and the heat absorbed by the water in this core is then used to boil water in what's called the steam generator. So there's two independent water loops in this. This doesn't always have to be water. Remember, this is just called the coolant. But as the coolant flows through here, it's extremely high temperature and therefore high pressure as it's coming through here. It comes in contact with liquid water inside the steam generator. The whole purpose is to boil this water, this blue water here, in the steam loop. Right? To maintain a high water temperature of up to 300 degrees Celsius in liquid form, the coolant is held at an operating pressure of about 100 atmospheres or higher. And in the pressurized water reactor, the core is contained inside of a pressure vessel. Well, there's actually a pressure vessel here. That's a high pressure vessel that is in turn surrounded by a primary concrete containment structure with actually, a lot of times this will be inside a pressure vessel. It'll be stored in concrete, and then there's a second kind of concrete containment structure. A lot of times with steel embedded in it as well. The primary weakness of the pressure water reactor is to maintain this coolant at the high pressure. If the pipe in the high pressure water circuit were to fracture, the water in here would no longer be at pressure because this room is not maintained at pressure. And so it would immediately flash to steam, and therefore it would lose its cooling effect. So we need to remove the heat here. And the temperature in the reactor then would cause a thermal meltdown. Therefore, although we're showing only one loop inside the pressurized water reactor, typical pressurized water reactors are going to have several loop systems that will engage in case the primary loop fails. So they'll have these emergency loop cooling systems. Right. The rest of the behavior of the pressurized water reactor is actually almost identical to the steam Rankine cycle plants that we kind of went through in detail earlier. We just see that there's a steam line that goes to a turbine generator. A lot of times, again, this is multiple stages. There's a cooling tower, a condenser pump, and it just continues that pumping action throughout the system. So I'm not going to spend any time going through that because it's almost exactly the same as in the generator. The real difference being in this one that there's this closed loop inside the pressurized water reactor. The second most common reactor is called the boiling water reactor, the BWR. In the BWR design, the water that acts as the coolant here and the moderator is allowed to boil into steam to drive the turbines directly. So you see what's happening here. We've got the control rods. We've got the pressure vessel. What happens is the heat causes the water to flash to steam. We've then got some a steam line. The steam line turns the turbine directly. There's the condenser unit right here. The condenser unit then pumps this condensed water back into the pressure vessel. So there's the it returns the water here. In this configuration, the turbines in the generator exposed to potentially radioactive coolant, but the elimination of the separate steam generator, and we see that this loop is eliminated as compared to this, so it's a much simpler system. The elimination of the separate steam generator reduces both the cost to construct this and then also the heat losses due to inefficiencies in this system. So again, two major designs: pressurized water reactor, most common in the United States, I think. We'll look at numbers in a minute. Boiling water reactor, a little more common worldwide, but still a fairly common design. Those make up the bulk of nuclear power plant designs. And more importantly, they kind of give you the idea that nothing super special in terms of new technologies is going on in here. It's the same as in the coal plant, right? In the United States, currently there are 100 operable nuclear reactors that are organized into 66 different electric power plants. It looks like we've got 35 boiling water reactors and 65 pressurized water reactors. The smallest smallest plant is 478 megawatts, and the largest is we've got a 1,300 megawatt reactor. plant. It's grouped in 3, and it produces 4,000 megawatts. So it's just a gigantic, power plant down here in the American Southwest. 4,000 megawatt total output. The next type of turbine we're going to look at is the use of the combustion turbine for electricity generation, and it's very similar to the steam turbine generators that we previously described. There's not a whole lot of difference, except in this case, again, we're using the Brayton cycle instead of the Rankine cycle, and therefore we're using a gas instead of a fluid, or a liquid, excuse me. So in a basic gas turbine, fresh air is drawn into a compressor, this kind of trapezoid here. Fresh air is being drawn in. Compressor, a spinning rotor blade compresses the air. It elevates both temperature and pressure. So this compressor can exhaust just hot air, basically. This hot compressed air is then sent into the combustor, and it's mixed with a fuel. This can be natural gas, kerosene, liquid propane, oil, anything like that, and it's burned inside this combustion chamber. The hot exhaust gases from the combustor are then expanded across the blades of a turbine and then exhausted into the atmosphere. The compressor and the turbine share a conducting shaft, so that a portion of the output energy from this exhaust gas that's spinning the turbine is actually used to drive the generator. Typical combustion turbines operate in about 30% output efficiency. In that previous design, a large amount of high temperature waste heat is just vented directly into the atmosphere. Typically this temperature is about 500 degrees Celsius. Modern designs add what's called a heat recovery steam generator, an HRSG. And its purpose is to capture that vented temperature. So we notice that this portion of what's called the combined cycle generation unit looks exactly the same as the simple cycle gas turbine or combustion turbine. What is then happened is, instead of just venting this high temperature gas to atmosphere, we're running it through a HRSG, the purpose of which is to capture this waste heat and run a steam turbine. The exhaust gases are going to pass through the HRSG. They then vent to the atmosphere. Sometimes you can bypass them. That HRSG boils water, creates a high pressure steam loop, high temperature steam loop, and then again that is expanded across the blades of a steam turbine. And then you see that there's a generator, there's a condenser, there's a deaerator, a pump, a cold water cycle, the addition of the cooling tower. So from here on over, this looks a lot like a traditional Rankine style steam plant, which it is. It's just the heat source is the exhaust gas from the combustion turbine. So this again is called combined cycle. And whereas this design here is about 30% efficient, this design here, these are really the most efficient power plants other than hydroelectricity. These clock in low 50s usually in terms of percent efficiency. In the United States, there are a little over 1,500 natural gas plants. About 1,200 of them are owned by electric power utilities, the rest of them being in the commercial and industrial sector. And the reason for that big difference, 500 natural gas plants, is that a lot of times there's natural gas that is the byproduct of some sort of industrial or commercial process. It either comes from a chemical reaction, it comes from the decomposition of materials. They have a waste byproduct that they can use, they can run through a gasification step, and they can produce their own gas. And so therefore they have an economic incentive to build their own natural gas plants to produce electricity. A lot of times landfills will do this. So this is becoming more and more common in the electric power system, where you'll put a cogen facility outside of the electric power sector. And that leads us to the last type of engine that we're just going to briefly discuss. It is the reciprocating or diesel engine. It's a piston-driven engine. It is the old, widespread, well-established technology that a lot of times has been called the internal combustion engine, reciprocating engine, etc. What these need is that there's an input fuel, there's air, and compression, and some sort of combustion source that causes the diesel cycle to occur. And depending on the ignition source that's used in the engine type, they generally fall into one of two categories, which are spark-ignited engines, typically fueled by gasoline or natural gas, or compression-ignited engines, typically fueled by diesel fuel. These commercially available reciprocating engines for power generation are usually pretty small, about 0.5 kilowatts to 6.5 megawatts in capacity, and they're used in a kind of a wide variety of backup applications due to their small size. They typically low unit costs, and they've got, a lot of times they produce a lot of useful heat, so you can use that too. So, the major applications are going to be prime power generation for remote locations, what's called peak shaving, providing power at the very peak of the electric demand curve. Most frequently, they're used as backup power plants or remote power plants. These engines also have the ability that they can run on fuel generated by waste treatment, such as methane. Often, a lot of times you'll find them at biofuel locations too, because of the ethanol. They also make up a large portion of the combined heat and power, which is called cogen market. So a lot of times you might need to create heat for a process and have some electricity. If you're using an engine to produce both process heat and to produce electricity, we call that cogeneration.